Today at Encyclopedia, we're delighted to be joined by Matthew Edwards from the University of Toronto Library, who is here to talk to us about his research. So, welcome, Matthew, and thank you for joining us.
Well, thank you very much, Joseph. I'm happy to be here talking to you.
Thank you for being here. So, before we start talking about your research, our viewers would like to get to know you a bit better. Would you be able to share a bit about your academic career and what drew you to astrophysics and theoretical physics, given your background in biology?
Yes, so my background is a little bit unusual for the physics and cosmology world because I started off in biochemistry and biology at McMaster University in Ontario, and I graduated from there eventually and wasn't interested really in physics and cosmology at all. I hadn't really experienced that much of it. But I did get interested in the origins of life. And through that, at that time, that was back in the 70s when I was going through uh, the whole discovery of DNA and RNA and the protein translation process was just new and it was fascinating. And it kind of immediately draws you into like, how could such a thing ever have evolved? And it turns out to be kind of a very interesting process in physics and chemistry and leads you into reading kinds of materials like even that start to lead you into stars, cosmology, the universe, especially with some of the Russian writers at that time. So that's how it started. I got interested in the origins of life, and I started developing models and started to try to publish on that, and eventually was able to do that. Got into it, and then that's how it began. While I was there, starting off in that field, I got into reading about uh, at the same time about gravity work by Georges Louis Lesage. It's called nowadays called pushing gravity, where masses are pushed together by like small particles or waves from all directions, and that sparked a big interest too. I got interested in all these things more or less at the same time, and then in cosmology, I got into read. I read this book, The First 3 Minutes by Steven Weinberg, which was like the sort of like the standard Big Bang model. And I was absolutely stunned that people could actually believe such a thing. And I'm still quite, kind of amazed that that theory is as popular and still so widely accepted as it is today. We'll get into talking about that later.
Sure, yes. Thank you for that introduction. That's a very interesting path that you've taken. We can talk more about your research now. You mentioned gravity and gravitational physics just then. So your work spans gravitational physics, cosmology, and geophysics as well, which is an interesting combination. So I think you may have touched on this a bit already, but what initially sparked your interest in these fields, and how do you
Oh,
see them evolving in the next decade?
yes. Well, the gravity kind of was like this focus on Lesage's theory, and this thing of gravity is really caused by masses being pushed together by something. Okay, and I actually got heavily into that at the university at library where I was, and eventually edited a book on that called Pushing Gravity, which brought together a lot of different people's theories about that from the past, and there are also people still working on it. And that book still gets a lot of attention, not from the mainstream so much, but a lot of people working outside of it. Now, I kind of things kind of stalled out a little bit in gravity work, and I got into looking at some other problems related to geophysics, and there was a particular problem with why do planets emit as much heat as they seem to? Like I'm talking about Jupiter, Saturn, and even the Earth has emitting more energy than you might expect. And I stumbled upon a mechanism to account for it, and that mechanism has been the center of what I've been doing really ever since. And it's just that you can say that the if you take the internal gravitational potential energy of an object, uh, for example, for the Earth, it's proportional to the square of the Earth's mass times the gravitational constant, and the divided by the Earth's radius. That's the internal gravitational potential energy, and multiply that by the Hubble constant. That gives you a heat uh, radiation term. And that's what initially I called that the Hubble luminosity. I've recently changed that name to the Lambda luminosity because it has a cosmological connection as well. And so I've subsequently connected this Lambda luminosity to gravity work because well, let me back up just a moment and say, well, how can this even happen? How can this lambda luminosity even work? And what I've come up with or concluded is that you can think of you need to have a sort of a model of space time itself, and the model is every object in a visible universe, observable universe, is connected by these strands of photonic energy. Uh, I, some authors have worked on this as well. In particular, Arto Anila and his group have described these filaments as graviton filaments, but the gravitons are themselves pairs of overlapping photons. So it's really all electromagnetic, and so the whole universe is connected with these electromagnetic filaments that stretch the whole radius of the visible universe. And so that's the basis. That energy is being turned over, exchanged. It's being lost. It's being regained. It's a static system. So that's sort of the basis of the general basis of my work. This lambda luminosity, and it relates to cosmology, black holes physics. It relates to geophysics, and it relates to gravity, how the basic gravity mechanism works. It all goes back to this one thing.
Excellent. Thank you very much for outlining the basics there. You mentioned black holes. If we can talk a bit more about those in detail. Could you explain how black holes and the shell black hole universe function in your model? It
Sure.
seems that this would be an exciting development in black hole research if confirmed, but it also seems rather controversial and has drawn some criticism. So you can now briefly address those criticisms as well.
Sure. Well, thank you very much for that opportunity. So how it started off with black holes, uh, I had done all this work on, with my gravity model. I had a gravity model based on this lambda luminosity, and I was what to do next with it. I said, well, I haven't really looked at how black holes function. I actually had a kind of a very hazy notion of how how real black holes even are in terms of the singularity and the properties that are usually ascribed to black holes. So I thought, well, I should be able to do something with my gravity model to explain black holes. And then I got onto this trend in black holes research to view it as shell structures being kept sort of stabilized by some sort of inner fluid, quantum fluid of some kind. It gets to be very complicated mathematical stuff. And it was at that point that I realized that if you just again take my very simple equation, lambda luminosity, and apply it, let's say, let's say that the universe, a big problem in cosmology is where's the dark matter? Where's the dark energy? I'm talking about the standard model. They don't have any clue about what these things are. They're constantly trying to invent things. Now, what if, though, the universe is in the form of a black hole universe with a rather thick outer shell? It's way off at the distance where only now the James Webb telescope is starting to see it, to see stuff out there. And if all that extra mass is just simply located out at that, say, one third of the distance away from the edge, the Hubble distance. So it's really a shell structure, and we would be in a less dense part of the universe, somewhere in the middle. And with the Hubble luminosity or the lambda luminosity now, that energy that's released in that is exactly is exactly the right amount to keep that universe from collapsing down into a singularity. So with that simple equation, I could do away with all those other theoretical fluids that theorists were using to explain black holes, and and explain black holes that way, but also as a bonus, explain how the universe itself is functioning, because the universe is a one of these shell black holes. Black holes are just the same. Now, in a case of an ordinary black hole, there's a rotation there. And so there will be a tendency for it to collapse down into a torus, but it's just the same physics involved of the Hubble luminosity or this lambda luminosity keeping the whole thing inflated.
Right.
Now, concerning the criticism that I've been up against, there was a particular video that Sabine Hossenfelder did about my work, and here was the thing with my model. It, for me, explained how black holes in the black hole universe would work, but for the average physicist out there, they're still looking for an explanation that's rooted in general relativity, which I did not have. There's also in general relativity or even in Newtonian gravity, if you have a shell structure, inside the shell, there's no gravitational fields. And so it's at first I thought, well, that's a nice thing because that's what the way things sort of seem to appear. However, it it didn't really it didn't really address certain other features. And I tried to publish my paper without really going into the general relativity aspects of it at all, and I was only getting a limited response. So I had many journals decline my submission about the black hole shell universe. And but then I looked into finding these. Some workers had done work in general relativity, found new solutions. In particular, Jun Ni in China found a set of solutions um, for neutron stars, which sort of implied that they could be stable as shell structures, which totally different. He did his integrations of these Einstein field equations in a totally different way than had previously been done. And Juni's equations were then picked up by Lubos Neslusan, Jorge de Lira, and others, and they formed a kind of a different picture of what's going on inside these shell structures. And what's different about them is that um, first off, they're stable, but and secondly, they do have a gravitational field inside. So there's actually like a redshift of let's say light moving away from the shell is going to be red shifted, light moving towards the shell is going to be blue shifted. And the thing about Sabine Hossenfelder's video was that she looked at these knee solutions and did some pretty thorough analysis on it. She felt that they didn't really explain fully how these structures could form in the first place or be stable afterwards, which I would be in disagreement with that statement itself because from the work of these authors themselves, they are stable structures under these equations.
Well, thank you for going into some of the details there.
Yeah.
But speaking of the Earth, you have done some work in geophysics as well, including plate tectonics. So, what insights from geophysics do you find the most relevant to your theoretical work?
Well, it's um, in geophysics, there's the theory that we have now is plate tectonics, where there's heat coming up from the Earth, uh, material moving up in plumes and in mantle convection, and then uh, the slab the crust has it forms into slabs which dive down and sink down into the uh, interior of the Earth in a cyclic process, and that is thought to be the thing that moves continents around for decades now. And there's certain things that are true about that, but it's been a there's kind of a big gap in the energy that's really required to do that, and the energy sources that they call upon to do this, which is radioactive decay, leftover heat from the Earth's formation, and a few other things. And related to the other work that I was talking about, related to the Hubble luminosity, or this Lambda luminosity, I'm now calling it. This is an enormous amount of energy that can be released inside the Earth due to this Lambda luminosity, and more than enough to drive this plate movement. But there's an extra added feature in it that makes it all work. Is that it has enough there's enough energy here to actually increase the Earth's radius slightly. I mean, it is really slight, like about zero point 0.1 or zero point 0.2 millimeters per year. And there's been a number of researchers that have found that this could actually be happening. Their measurements actually show this. In particular, Wenbin Shen at Wuhan University and his colleagues have published a number of papers showing that this uh, evidence for this. It's still in an area where we have to refine it, get these measurements really as accurate as possible. But there's a lot of evidence there already that the Earth could be increasing by this very, 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 very tiny amount. But the amount of energy required to do it is huge, and the Hubble luminosity could account for it. Now, here's the thing: how do if the with the deep mantle, the energy is generated, a lot of it in the core, because that's where most 1/3 of the Earth's gravitational potential energy is. And so there's a lot of heat coming up from the core. And as it's going up through these deep mantle plumes, which I now know go right down to the core, it's bringing up energy material at a higher density, and it's going up past this barrier at a line that's about 670 kilometers below the Earth's surface. Material is moving up past that, and as it comes up, it ends up recrystallizing at a lower density, like so it's expanding a little bit. But the slabs that are supposedly in plate tectonics moving down to the core to balance this, they're not all going down to the core. They're stalled out at this 670 kilometer line. So if that's true, the flows of mass are not balanced. There's more mass coming up to the upper mantle, but because it's lower pressure there, it's recrystallizing, and that's causing the Earth's slow expansion. And this is really the driver of geology. It's not radioactive decay is rather a small player in it. This is way, way bigger and has a lot more potential to do stuff.
So, given your interest in astrobiology and biology, do you believe that we're closer to finding extraterrestrial life, especially with recent exoplanet discoveries?
Well, I mean, that is the big question nowadays, with the Webb telescope able to look so far out and it's so close up on individual planets. And just recently, there was a paper coming out that they saw some sulfur compounds in the atmosphere, which suggested possible life being arising on this planet. I personally feel that these a simple thing of gas signatures are not enough to really get too excited about. Um, I I've on one hand, we've got so many planets out there that they now know that most stars have got planets around them, and there's a lot. The Webb has found out that there's a lot of Earth-like planets, and so there's like literally billions of planets out there. And you'd think, okay, well, surely the, the odds are almost, astronomical that there would be other life forms out there. But we don't really know yet how life formed on our planet, as I was describing earlier. People just tend to gloss over that what an amazing thing that it is that molecules can form on the Earth and interact to form these intricate cellular machines. If you think about the possibility of that happening, it's almost infinitesimally small. So, like, we got an infinitesimally small number against an infinitesimally, or no, a huge number. It's a maximally huge number. So they cancel out. We're left we're left without really much clue as to whether there's other life out there or not. Now, I can add that we are there are some clues that we are getting closer to finding the origins of life, and this relates again to work that I did some years ago. It has to have been on a mineral surface, and it almost surely was a metal sulfide surface, most likely pyrite. This is the only way that you can have a system where molecules can grow as polymers and interact with each other to become more complex. That's where we are. I'm not too optimistic that we're going to see a sign of life out there. It's yes, keep looking, but I think it's a hard thing. Origins of life is a very hard problem. We're not close. We're not really close to it yet.
Wonderful. Thank you very much. What advice would you give to young researchers looking to enter theoretical astrophysics or interdisciplinary physics today? Are there particular skills or mindsets that you think are essential for success in these fields?
Well, as you will have heard throughout this interview, is that my actual background in theoretical physics is slim. What I've had, though, that other theoretical physicists and cosmologists don't have is this biology factor that shaped my work to a certain extent. So what I'm giving is not the advice that other theoretical physicists would give, because it doesn't obviously always apply. What you have to do is bring ideas from outside the nitty gritty stuff that you're reading, that students are reading related to these whatever fashionable things are string theory or whatever, and try to bring in, try to think bigger, try to think bigger than the little things that they're teaching you in your cosmology and theoretical physics courses. So, for my advice for younger people is don't get bogged down too much in those fine theories that people spend years working on. Try to broaden yourself read up on some other stuff outside of physics. Read up on other fields. That's the best thing you could do. Even read up on some geophysics. It's bound to be relevant.
Absolutely. Thank you for the valuable advice there. And thank you for taking the time to speak with Encyclopedia today about your fascinating research. It's been a pleasure.
Well, thank you, Joseph. It's been a real pleasure also. Um,
Thank
I'm
you.
happy.
Goodbye.
Okay, bye.